Well, good afternoon, everybody. This is John Stewart. I hope everybody can hear me.
I can hear you, John.
Terrific. Thank you, Kristen. Well, thanks for joining us today. Our speaker is Mike Greenfield, who did his PhD with Steve Kramer. Steve will introduce him in just a moment. So I just want to thank Mike for preparing the presentation. This is about a unique set of case histories that Mike developed with Steve and others as part of his PhD thesis and is already in the NGL database. So I'm looking forward to the presentation, and I think this will be of great use to our community. And I think at this point, I'd like to hand it over to Steve Kramer to introduce Mike.
Well, thanks, John. It's a pleasure for me to introduce a former student, Mike Greenfield. Mike came to the University of Washington with already a master's degree from Virginia Tech and several years of experience, which proved to be very helpful in his work. He was also unafraid to take on challenges and dealt with looking at a number of liquefaction case histories with emphasis on considering the timing of liquefaction, and developed a number of procedures for looking at ground motions recorded at liquefiable sites and interpreting them in order to determine the time at which liquefaction was triggered, and use that to be able to do some additional interpretation of case histories that we can't get from the normal kind of binary yes or no indications of whether or not liquefaction had occurred. He did field work in Japan as a part of this, and a lot of numerical and analytical work here. He is the president, CEO, and chief bottle washer of Greenfield Geotechnical, now in Portland, Oregon. So, Mike, I'll give it to you. Thanks very much for preparing this presentation for us.
Thanks, Steve. Since I can share the slides, I'll begin. There we go. Oops. Okay, hopefully everybody can see my slides now. You guys see my slides?
Yep, I can see them.
Okay. Well, thank you, Steve. I appreciate the kind introduction. As he noted, I have been working with the Next Generation Liquefaction project, developing a data set of case histories at locations where we have observations of liquefaction and co-located strong motion records. And this presents a unique opportunity to evaluate ground motion modifications due to liquefaction, which I want to talk about today. So the objective of collecting this case history data set is to support liquefaction triggering modeling. And there's a few aspects of case history that need to be considered in order to be useful for a liquefaction triggering model. First, we need some estimate of the cyclic loading at the time of the earthquake. That's usually in the form of some estimate of the intensity of shaking, conventionally PGA, and some approximation of the wave mechanics, so we can estimate the stresses at the depth of interest. And that's usually approximated in the form of a R sub D parameter. We also need some observation of the manifestation of liquefaction or lack thereof. And typically that's in the form of sand boils, lateral spreading, some superficial observation, and that's then used in a binary sense to develop a decision function that separates the case histories where liquefaction has been observed from case histories where we see no evidence of liquefaction. We, of course, need some measurement of subsurface properties as well, including measurement of the groundwater depth, some determination of the liquefaction susceptibility. Does the soil behave as sand-like, and is it susceptible to liquefaction? We need some measurement of the relative density of liquefiable soils or the cyclic resistance of the soils, and that's typically estimated from penetration resistance, either CPT or SPT. We also need some approximation of the soil mechanics. For example, the K sigma parameter that's used to account for the contractive nature of soils with high overburden pressure. So each one of these aspects of a case history can be highly uncertain. And the benefits of evaluating liquefaction case histories at strong motion recording stations is we can actually reduce the uncertainty in every one of these aspects. So with respect to cyclic loading, we can directly observe the intensity of shaking at the site because we're measuring the ground surface acceleration. There needs to be some modifications to account for the instance of liquefaction. Liquefaction modifies the ground motions, as I'm going to describe here in a bit, but we at least have some direct observation of the intensity of shaking. The recorded ground motion also serves as a target for numerical analyses, and that helps us better understand wave and soil mechanics associated with liquefaction at the site. Interestingly, though, just having a recorded ground motion does more than just help us approximate cyclic loading. It can also help us reduce some of the uncertainty in observations. Liquefied soil is very, very soft, and so there's a rapid shift from the stiffness of the soil before liquefaction is triggered, after it has been triggered, and we can observe that in the ground motions, and that helps us observe if liquefaction has actually indeed occurred at this site. Sometimes there's a question as to whether or not liquefaction occurred. Either no one was able to get out to the site until several days after the earthquake, or the evidence of manifestation could be attributed to something else. Having a recorded ground motion actually helps us confirm the observation or lack thereof of liquefaction. Having a recorded ground motion can actually help us reduce the uncertainty in subsurface properties as well. And this is not necessarily intuitive, but once we have a recorded ground motion, we have a target for conducting numerical analyses, and we can use that target and vary the subsurface properties to evaluate what properties are necessary to reproduce the ground motion that's been recorded. And I'll talk a little bit about that with respect to a few case histories today. So because of the value of these case histories, NGL has paid particular attention to observations of liquefaction with collocated ground motion recordings. So there's 22 sites that are currently in the database. Most of these are from Japan. 18 of the sites are from Japan, and 4 sites are from California. And several of these sites have been shaken by multiple earthquakes, some triggering liquefaction, and some triggering liquefaction multiple times in a few of these locations. The database, the data set, has earthquakes ranging all the way back, or dating all the way back to the 1964 Nagata earthquake, and as recent as the great 2011 magnitude 9.1 Tohoku earthquake. Looking at the distribution of earthquake moment magnitudes and rupture distances from these case histories, we see we have a set of case histories that represents a fairly wide range of earthquake magnitude, all the way from magnitude 6 up to the Tohoku 9.1 magnitude event, in a large range of rupture distances as well. Some sites very close to the earthquake rupture, and some sites that are also very far from the energy source, particularly from some of the Great Subduction Zone events in Japan. From this data set, I want to focus in particular on 3 example case histories today. So the first example I'm going to talk about is the very well-known wildlife liquefaction array. We have some new tools, or relatively recent tools, that we can use to take another look at this site. I'm going to talk about a site in Japan, IBR 14, that was shaken during the Great Tohoku earthquake. And I'm going to end today with a revisit to a case history from the Nisqually earthquake, which is coming up on its 20th anniversary in February here, a case of liquefaction at Harbor Island. So the first case history I want to take a look at here to just illustrate the value of these recorded ground motions at liquefaction site is the very well-known wildlife liquefaction array. So this is a site that had liquefied in previous earthquakes. Following the Westmoreland earthquake, a number of instruments were installed at the site, including a ground surface strug motion recording station, illustrated by this green circle here, and a downhole strung motion recording station, illustrated by that second green circle. And so the site is generally characterized by a layer of silt at the ground surface, relatively shallow groundwater, and then a layer of silty sand extending from a depth of 3 meters down to a depth of about 7 meters. The silty sand is susceptible to liquefaction, it's saturated, and you can see in the cone tip plots that it ranges in relative density from loose to medium dense. So certainly susceptible to liquefaction and could liquefy during strong shaking. Well, 2 earthquakes shook the site in 1987. The first earthquake was the magnitude 6.2 Elmore Ranch earthquake. And this earthquake did not produce liquefaction, and there was no observation of liquefaction at the site. And you can see in the surface and downhole acceleration time histories that these time histories have a relatively consistent trend with each other. Early in the motion, we see an increase in amplitude as S waves start to arrive. And then towards the end of the motion, as the amplitude of the acceleration decreases, we get a lengthening of the period of the ground motion, so a decrease in frequency content as surface waves start to dominate the motion. And that's apparent in both the surface and the downhole recording. Just hours after the Elmore Ranch earthquake, the Superstition Hills earthquake shook the site and did produce liquefaction and lateral spreading. The downhole recording shows a similar trend as the Elmore Ranch earthquake, an increase in amplitude in the beginning of the motion, followed by a gentle decrease in amplitude and a lengthening of the period of the motion. However, the surface motion between that liquefiable layer, something happened to cause a rapid shift in the frequency content of this surface motion. So right around 13 to 14 seconds into the motion, there's a rapid shift in frequency content. And then afterwards, we see these spiky pulses occurring. Looking at the spectral amplification between the downhole, so this is a plot of the spectral acceleration at the surface divided by the spectral acceleration at the downhole array, an estimate of how much modification to the ground motion that layer of silty sand is contributing. We see a very large difference in the spectral amplification from the Superstition Hills earthquake compared to the Elmore Ranch earthquake. So they're more than 2 times the amplification at these longer periods, indicating there's very low frequency amplification occurring, possibly due to liquefaction at this site. We'd like to take a closer look at the evolving frequency, the evolving amplification that's occurring over time during these 2 earthquakes, or in particular the Superstition Hills earthquake. So we can use some time frequency analysis tools to decompose the motion into its frequency components over time. So one of these tools is called the Stockwell Spectrum. And as you can see in this figure, starting with a relatively low frequency wave transitioning to a high frequency wave here, the Stockwell Spectrum does a good job of capturing the frequency content of this first wave. the abrupt shift in frequency content that occurs right around 5 seconds, and then the frequency content of that second wave. So this transform provides a nice balance of accuracy in terms of frequency content and accuracy in terms of time shifts in the potential frequency content. Looking at the ratio of Stockwell transforms at the ground surface compared to the downhole, so this is a measure of the transfer function between the downhole and surface array. We see, with the exception of some early high-frequency amplification in the motion, for the duration of the motion, in general, there's significant amplification, or the peak amplification is occurring at a frequency of about 5 hertz. You see the first band of the transfer function here. The second mode of the transfer function shows up to some degree up here at about 10 to 15 hertz. A similar trend can be observed during the early part of the Superstition Hills earthquake. So we see peak amplifications occurring at frequencies on the order of 5 hertz. The second mode of amplification occurs, you can see that at 10 to 15 hertz. Well, then right around 15 seconds, there's a rapid shift in the amplification that's occurring. So instead of the peak amplification at a frequency of 5 hertz, the motions at a frequency of 0.4 to 0.5 hertz, or even lower in some instances, is being amplified. So this is a rapid shift in the stiffness of the soil between the downhole and the surface recordings is producing this large amplification that's occurring at this time. This shift corresponds well with other types of time and frequency analyses. So for example, with respect to cross-correlation analyses, so this is a measure of the arrival time of waves as they're coming into the downhole array compared to the waves as they're arriving to the surface array. So we can measure the travel time between the downhole and surface array using cross-correlation analysis, and then estimate the average shear wave velocity between the downhole and surface recording. This corresponds very well with that rapid shift in frequency content that's observed in the Stockwell analysis. So the Stockwell analysis has multiple lines of evidence suggesting that it is indeed capturing the shift in frequency content that occurs at this specific time. Well, the question is that due to liquefaction? Does that shift in frequency content occur because of liquefaction? And so a group in 2014 did a really excellent job of using the recorded ground motion at the surface as a target for back calculating subsurface properties. So by inputting the downhole ground motion into a finite element profile and adjusting the soil properties until they matched the surface recording, we can estimate this. We now have a calibrated model that we can use to estimate the shear stresses and strains, generation of pore pressure during shaking. And what this model suggests is also that a rapid shift in frequency content occurred. The soil became very soft, and very likely liquefaction occurred at that time of around 13 to 14 seconds into the motion. So a few observations from the wildlife array. Downhole rays are, of course, extremely important for us to understand how waves propagate through the soil. We can directly observe changes in soil stiffness when we have these downhole arrays. So this is these are gold. Time frequency analyses are also useful to help us interpret if liquefaction occurred at a site. So based on the time frequency, based on the time when the shift in frequency content occurs, that time corresponds well with liquefaction triggering in numerical analyses and the changes in soil stiffness that we see due to liquefaction. One other takeaway from this wildlife liquefaction array is that numerical analyses help us to see inside of the site. Once we have a well-calibrated numerical analysis, we can evaluate the evolution of cyclic stresses, strains, and pore pressures that occur during shaking. So the second case history I'd like to take a look at is a strong motion recording station in Japan, Ibaraki 14, which was shaken during the 2011 magnitude 9.1 Tohoku earthquake. So of course, this earthquake was very long in duration. I could see strong shaking started at around 30 to 40 seconds and continued well after 180 seconds in this motion. In this recording, we also see a rapid shift in the frequency content of the motion. So as the amplitude of the motion increases, it hits a peak, and then we see a rapid shift in the frequency content of the motion, and some of those spiky pulses, again, occurring after liquefaction has been triggered. Taking a closer look at that acceleration time history using the Stockwell Spectrum, we can see again that there's a relatively consistent frequency content before this time we have this red line drawn, so a relatively consistent frequency content early in the motion, and then a rapid shift in the frequency content right around 110 seconds into the motion, followed by a consistent low frequency signal for the duration of the ground motion. So this presumably is the time at which liquefaction could have been triggered. We get a rapid shift in the stiffness of the soil, and the soil can no longer transmit high frequency waves to the ground surface, and low frequency waves are amplified, causing a rapid shift in the frequency content of the motion. So there's a number of other considerations at this site. It's not necessarily as clear as to what happened at this site as it was at the Wildlife Liquefaction Array, which has some of its own considerations. But we can use some of the tools that we learned about from looking at the Wildlife Liquefaction Array to help us investigate this site in a little bit more detail. So satellite photos taken shortly after the earthquake show ejecta in this parking lot down here, but no observations of ejecta or surficial manifestation of liquefaction right around the strong motion recording station, which is at the north end of this parking lot. The site is located on a modest slope, which slopes from the west to the east. This upper parking lot is cut into the hillside with a little bit of fill to grade the parking lot, and this lower parking lot is likely founded on a little bit of fill. Looking at a photo just after the earthquake occurred, so the ejecta in this lower parking lot is still moist. You can see the strong motion recording station up there, and no evidence of liquefaction in that upper parking lot. The gear reconnaissance arrived at this location shortly thereafter, and there's still evidence of ejecta in this lower parking lot, large longitudinal cracks and sand still in this lower parking lot, as well as cracks in the upper parking lot indicating some deformation occurred, but no ejecta. So we have a rapid shift in the frequency content of the ground motion. We have liquefaction nearby. We have deformation at the ground surface. So what exactly happened here? Because of the value of these strong motion recordings and to help clarify this site, NGL pursued a subsurface investigation at this site. So I went out there with a team of Japanese colleagues to do a boring down to a depth of 30 meters, take penetration resistance measurements. We actually measured the energy associated with these penetration measurements. We used the SPT analyzer to measure the SPT energy, which is somewhat variable. At this site, it ranged from about 72 to 82% of the theoretical energy. So measuring the energy associated with SPT is a very important consideration when we're looking at these types of case histories. We also performed a CPT and have cone tip and seismic velocity measurements. So the subsurface profile at this site consists of a thin layer of fill at the ground surface, followed by a layer of clay and clayey sand to a depth of about 7 meters. The subsurface investigation encountered fairly high groundwater at a depth of about 2 meters at this site. Below a depth of 7 meters, silt extends to a depth of about 17 meters, followed by interlayered sand with silt and silty sand deposits. The first step in a liquefaction triggering analysis is, of course, to determine if the soil is susceptible to liquefaction or not. And this near-surface clay and clayey sand falls into the moderately susceptible liquefaction category. Certainly the sand with silt and silty sand below a depth of 17 meters is susceptible to liquefaction. But the susceptibility of this near-surface clay sand is moderate. It's not clear whether it's susceptible to liquefaction or not just by looking at the plasticity index information. So we have a situation here where we don't know if this near-surface clay and clay sand was susceptible to liquefaction. Certainly during the very strong shaking associated with the Tohoku earthquake and tip resistance on the order of 40 kPa, this could be, or 40 TSF, I guess. This could be susceptible to liquefaction and could liquefy during the strong shaking, but it's not clear as if it was susceptible to liquefaction or not. So one option to help clarify the subsurface conditions or provide one more line of evidence is to conduct parallel sensitivity analyses using finite element for these moderately susceptible soils. So this site is a little bit different than the wildlife liquefaction array. We don't, unfortunately, have a downhole recording, but we do have a number of tools we can estimate the intensity of shaking at a similar rock outcrop near IBR 14. So, of course, there are ground motion prediction equations that we can use to estimate a target spectrum. We can even use the event-specific adjustments for these GMPEs, but particularly to the Tohoku earthquake, there's a large regional variation between some of these recording records. So we felt it was also important to consider a regional variation or a regional residual when looking at this station. So this residual takes the form of evaluating or developing a spectral acceleration from the event-specific GMPs, and then using the recorded motion at these other sites to estimate a regionally specific deviation from the Tohoku adjustment factors to the GMPE. So once we have an appropriate outcrop target spectrum, we can then, of course, select ground motions that represent the intensity of shaking at a rock outcrop and conduct parallel finite element analyses. These analyses show that if we consider the near-surface clay sand as susceptible to liquefaction, we get a fairly poor match with the recorded ground motions. So if that near-surface clay sand was susceptible to liquefaction, it's relatively loose to medium dense, and if it liquefied, it could no longer transmit high-frequency motions to the ground surface, and very likely there would have been a much lower spectral acceleration that would have been recorded if that near-surface clayey sand was susceptible to liquefaction. On the other hand, if we consider it not susceptible to liquefaction, we get a pretty relatively decent match with the recorded ground motion. So that gives us a line of evidence that that near-surface clayey sand was not susceptible to liquefaction. What that implies then is that liquefaction must have occurred very deep at this site. Something caused that rapid shift in the frequency content of the motion. It was very abrupt, it was very significant, and liquefaction at a very deep depth below 17 meters deep, could potentially explain that recorded ground motion. Well, this presents a very unique situation then. We have a recorded ground motion where we don't necessarily have strong evidence of surficial manifestation indicating liquefaction at depth. This implies that this could be one of the case histories with the greatest overburden pressure in our liquefaction triggering data sets. So looking at histograms of the effective overburden pressure from the Chetan and Boulanger and Idris SPT and CPT data sets, this deep instance of liquefaction presents a case history that has a higher overburden pressure than any of the other case histories. And that's largely due to this ability to use the recorded ground motion to see what sorts, to observe a rapid shift in liquefaction or rapid shift in the frequency content of the ground motion, and then infer that liquefaction could have occurred based on a very deep layer of sand and sandy silt. So a few observations from this case history. One, we don't necessarily need a downhole array to conduct these time frequency analyses. When they show a rapid decrease in frequency content, that could potentially indicate liquefaction is triggered. We can use our nearby ground motion recordings to create a regionally specific rock outcrop spectrum and input that into the numerical analyses. And that helps us, again, to see inside of the site and evaluate the evolution of pore pressure over time. And then to address that uncertainty in subsurface conditions, parallel sensitivity studies can help us clarify what the subsurface conditions could be. This needs to be conducted in parallel or with other sorts of our conventional geotechnical investigations and other studies as well. But this provides one more line of evidence towards a potential layer of soil liquefying. I wouldn't say it's the only source of evidence you should rely on, but it provides one more line of evidence that we can use to really develop or really reduce the uncertainty in our case histories. So the last case history I'd like to talk about today is liquefaction on Harbor Island in Seattle. I wanted to address this case history in particular today because we're coming up on the 20th anniversary of the Nisqually earthquake. And some of this information was really well documented at the time. There was a large team of seismologists and engineers who went out and documented and made maps of liquefaction features, but some of that information is starting to disappear over time. There are really excellent maps of liquefaction features mapped throughout SoDo, southern downtown Seattle, and Harbor Island, but I'm told they exist, but they've disappeared. We're currently looking for some of these in the archives at the UW Library and other places, but this information disappears over time. And it's important to get this into a permanent repository like the Next Generation Liquefaction project. So that information aside, this case history was shaken by the 2001 Nisqually earthquake. Harbor Island was shaken by the Nisqually earthquake, which was a deep interslab earthquake that had an epicenter near Olympia. Because of the depth and the basin associated with the Puget Lowlands, you can see that there was strong shaking across a fairly wide geographic area, all the way up to Seattle. Seattle, of course, has a number of strong motion recording stations and did at that time. Two of the strong motion recording stations I'd like to look at in a little bit more detail. The first recording station is located in West Seattle, and it's founded on glacially overridden soils. So these soils tend to be fairly dense. The shear wave velocity in the upper 30 meters of the soil is almost 400 meters per second. Conversely, Harbor Island is a man-made island located at the mouth of the Duwamish River. So over time, the Duwamish River has deposited a thick alluvial sedimentary deposit at the base of the mouth of the river. And then in the 1890s and early 1900s, a series of hydraulic filling projects filled in the area around Harbor Island and created this man-made island. This hydraulic fill is, of course, very well known to be susceptible to liquefaction and could potentially liquefy during even modest ground shaking. So we have a very bad player at Harbor Island here. What's also exceptional about this Harbor Island case history is there's actually a seismologist at the site during the earthquake. So this is there are no other case histories like this where we have a strong motion recording, a credible seismologist at the site who is there to work on the strong motion recorder, and some evidence and a narrative I'm going to read to you. So Bob Norris of Pacific Northwest Seismic Network says, during the earthquake, I looked up and saw the high tension wires overhead swaying with their support poles leaning back and forth, and I realized this was not only an earthquake, but an unholy big earthquake. When I stopped gawking and resumed intelligent thought, I remembered the wires overhead and gunned the truck into an open area. When it eased enough for me to be able to look around again, perhaps 25 to 30 seconds after the strong shaking began, I saw a dozen or so 60 to 70 meter tall cargo cranes that lined the waterways of Harbor Island quivering and flexing in place, resembling huge steel giraffes trying to dance. So Bob observes very strong shaking at this location. He checks himself to make sure he's okay. He asks some people around them to make sure they're okay. And then he remembers the strong motion recorder, which he was there to download the data anyway. So about 15 minutes later, he goes to download the strong motion record to get it out to the engineers and other seismologists as quickly as possible. And he says, I was distracted by a wet swishing sound coming from the ground nearby. I looked over to its source and saw a smooth dome of brown fluid. The dome lasted perhaps 2 seconds, then grew and burst into a muddy geyser. I confess I didn't think it was a liquefaction feature at all. The delayed onset, the limited amount of sediment in the water, and the high flow rate convinced me it was a water main break. In fact, I was annoyed because I thought the growing pool might engulf the driveway and prevent me from downloading the accelerometer data. After learning that this was indeed a sand blow, I returned to the site as soon as time allowed, about 3 days after the quake. So we have a credible eyewitness observe a sand boil at a recorded strong motion location. This is a great case history. We can compare the recorded acceleration time histories and response spectra of West Seattle and Harbor Island to observe if there was some modification to the ground motion. So looking at the West Seattle ground motion and spectral acceleration, the resulting spectral acceleration lines up fairly well with the most recent NGA subduction ground motion models. So this is considering the shear wave velocity, the basin depth, the deep aspects of the subcrustal earthquake. And the recorded ground motion lines up fairly well with the most recent GMMs. However, this recorded ground motion on Harbor Island exhibits very large amplification at about 1.5 to 2.5 seconds. So 4 times greater spectral acceleration than the GMMs would predict for a site, presumably where liquefaction did not occur. So no wonder Bob saw those giant gantry cranes flexing and dancing in place like huge steel giraffes. There's a huge amplification right at the fundamental period of a large structure like that. Looking at those time histories in greater detail using our time frequency analyses, we indeed see that there is a shift in the frequency content of the ground motion that could indicate liquefaction has been triggered. And the third piece of information we need to make this into a case history is subsurface data. So one aspect of this case history is only relatively recently has some of this subsurface data became available to the public. Washington Department of Natural Resources has released a huge set of subsurface information throughout Washington. And there's a number of subsurface investigations in and around Harbor Island that we can use to evaluate the subsurface properties. Of course, it would be nice to have a few more at the site with better shear wave velocity measurements, although Ray Chucker with DNR did do a MASW study at this site, so we have good shear wave velocity information as well. But the site is generally composed of that hydraulic fill at the ground surface extending to a depth of about 4 meters, relatively shallow groundwater. The hydraulic fill is about medium dense. And then the silty alluvial sand extends from a depth of about 4 meters down to a depth of about 9 meters. At this location, it's medium dense to, I'd say medium dense, with fines content ranging from 10 to 20%. Below a depth of 10 meters, the medium dense silty sand starts to become denser, with penetration resistance values on the order of 21 to 28 blows per foot. So we have two potential layers, or really three, that liquefaction could be triggered. So we have this upper hydraulic fill with a penetration resistance ranging from about 12 to 16 blows per foot. We have this medium dense silty sand alluvium with penetration resistance ranging from about 11 to 24 blows per foot, but it's a little bit silty. So there's a silt component, there's a fines correction that needs to be accounted for. And then we have somewhat denser sand with depth. So one of the ways we could potentially clarify which of these layers liquefied is to vary the subsurface properties until we get a profile that reasonably matches the recorded ground motion. So just like we did at IBR 14, we can develop a event-specific target spectrum, select ground motions, and then propagate them through a finite element profile. So in open seas, by varying the penetration resistance of the medium dense sand and loose silty alluvium, if we get to reasonably match, or the best match of the recorded ground motion occurs when we have liquefaction of this loose silty sand alluvium at a depth of about 5 meters. That produces the output response spectrum that's closest to the recorded ground motion. So this certainly helps us clarify where this case history may lie on our liquefaction triggering curves. If we just relied on some of these highly variable estimates, we may assume a different average penetration resistance of the site. Likewise, CSR varies with depth, so we might have a higher uncertainty in CSR. So really taking this approach of using the recorded ground motion as a target helps us to understand where this site may lie with respect to our liquefaction triggering curves. So this is a reasonably valuable case history. It lies close to the liquefaction triggering curves, and in particular with the fines content has significant leverage that could help define these liquefaction triggering curves. So a few observations from Harbor Island is we have an excellent, credible eyewitness account of liquefaction that actually had a delayed onset occurring near the station. Time frequency analyses indicate that the ground motions were modified, and that could be explained by liquefaction. Finite element analyses help us see inside the site to determine the critical layer, and that liquefaction most likely occurred in the alluvial silty sand. The results of the finite element analyses suggest that if that layer did liquefy, we could reasonably reproduce the modifications to the ground motion and the recorded ground motion at the ground surface. But this case history and the other Nisqually liquefaction case histories are not included in our conventional liquefaction data sets. So this sort of information is incredibly valuable, and I think needs to be considered when we're developing our liquefaction triggering models. Indeed, there's at least 12 more liquefaction strong motion records that have been influenced by liquefaction worldwide. 2 of these are in Seattle, following the Nisqually earthquake. There's 2 more strong motion recording stations. And in particular, look at SDS here. I mean, there's these huge pulses occurring after liquefaction. After the frequency content of the ground motion changed here around 38 seconds or so. And we see these huge pulses occurring as the soil dilates and contracts. There's a number of case histories in Christchurch that could be potentially useful, that show very low frequency content occurring after liquefaction has been triggered, and several case histories in Japan as well. So I thank you all for listening to my talk, and I'm very happy to answer any questions you might have about these particular case histories. So I'm going to open up the floor to anybody who might have questions about these particular case histories.
Thank you very much, Mike. I'll just remind all of the attendees that you're welcome to submit a question through the Q&A feature. If you'd like to ask your question verbally, you can raise your hand through the participants menu. You should be able to hover over your name and click the raise hand button, and then I can give you a chance to unmute yourself. I see that there's one raised hand. Scott Brandenburg, I will invite you to unmute yourself in just a minute.
All right, can you hear me now?
You're great, Scott.
Cool, thanks, Mike. Great presentation. I really enjoyed it. I had a question that was actually along the lines of that one acceleration record you showed in your last slide that had a really big dilation spike. Yeah, that SDS record. I've seen other ones like this too. I'm aware of one in Niigata from the, in Kashiwazaki from the 2007 Niigata Kinchuwatsu Oki earthquake. I can send you that if you want. But anyway, my question about that is that those high frequency spikes have a pretty huge impact on spectral shape. You know, they really bump up the PGA, because obviously the PGA is carried by that high frequency spike here, and that carries through all of the low short period spectral accelerations kind of out to the peak in the spectrum. So what I was wondering is whether you're using numerical models that can capture those kind of acceleration spikes. And I'm interested really in the way that you're developing a target spectrum and then, you know, running the simulation to match it to try and identify soil properties. And just wondering if you can't really capture those spikes, how that might propagate errors into that system identification problem.
Yeah, certainly that is a very excellent question. So of course it's important to model the physics as best we understand them when we're doing these finite element analyses. These dilation pulses not only can produce the PGA, but they occur at somewhat regular intervals too. So not only do they sometimes produce the PGA, but they also can cause huge amplifications at longer periods as well. For the Harbor Island is a good example too. And we see these are not quite as strong of dilation pulses. You can kind of see them in the north-south direction a little bit better. But these are occurring at a regular interval that lines up pretty well with that peak in spectral acceleration at around 2 seconds or so. So not only do they produce the PGA, they can amplify other components of the spectral acceleration. To answer your question about modeling, there's still significant uncertainty about the contraction and dilation behavior associated with these pulses. One of the ways we can address that is as I'm going through and adjusting some of the properties or trying to match the recorded acceleration response spectrum as best I can, tweaking some of those contraction and dilation parameters is certainly helpful. Another aspect that contributes to these dilation pulses is drainage. As if it's a relatively thin layer of soil that liquefied and it's able to dissipate pore pressures over time, we can see some strong dilation pulses or strong pulses as that soil layer undergoes contraction, generates excess pore pressure, and then some of that pore pressure leaves the layer, and you can see a rapid change in stiffness that way too. So this is still an area where there's, I'd say, very significant uncertainty in the behavior of these dilation pulses. And it is difficult to capture these really, really huge pulses. Case history is like, Harbor Island, where we still see these pulses, but they're not quite as large. The models seem to be able to capture those a little bit better. So I'm using typically PM4 sand or PDMY3 in open seas, and looking at both of those and seeing which of them are able to reproduce the acceleration response spectrum as best as possible.
Do you ever divide the spectrum time-wise? Like you create a spectrum before liquefaction and try and adjust properties to match that first, and then you know like which parameters you can play with to match the post-liquefaction part?
That's actually, I have not done that. That's an excellent idea. That is really a good idea. We've looked at the acceleration, divided up those, before liquefaction triggering and post-liquefaction triggering to just evaluate what some of the spectral amplifications are associated with liquefaction. But yeah, using that to adjust your target spectra is a really excellent idea. I have not, to this point, started doing that, but I think I will.
Okay. All right. Thanks again, Mike. I really enjoyed it.
Appreciate the question, Scott.
Looking for some more questions or any raised hands. Oh, I see one. Antonio, I'll unmute you in just a minute.
Hi, Mike. This is kind of maybe a pretty easy or pretty simple question. Looking at it as a structural engineer and having done some earthquake engineering in my time, is there any evidence or has there been any work done after the earthquake to actually go ahead and get borings for the site to see how much changes actually occurred in the site from a spot that maybe you knew something about versus after having an earthquake like this that causes liquefaction? I wonder how much the assumptions of what the site characteristics were before the earthquake have actually remained the same after the earthquake itself, based on that you see this transfer of material going up or down in these cracks and these driveways. It kind of gave me a thought to wonder if there's really any understanding of that, or if it's really not even it's a no, never mind, no, that wouldn't happen.
No, you have an excellent. You're on track there. So there has been. Is someone else talking, or is it you just have feedback? So there has been studies investigating this. Certainly, once liquefaction is triggered, and you have this ejecta, you have a situation where we're losing material from the site, and that could modify that potentially susceptible layer. And going in after the fact and investigating that could introduce some significant uncertainty in the soil properties before liquefaction is triggered. Even when there's not ejecta, if we have liquefaction, there's this resedimentation process that occurs within a liquefiable layer, where the bottom of the layer gets a little bit denser and the top of the layer gets a little bit looser. And so that's been investigated in a number of case histories. So that we can't really account for that, it's difficult to account for that with after the fact. I mean, we don't have borings everywhere, and if we want to develop these case histories, we need to have some subsurface investigation, and there is an additional uncertainty consideration when we have liquefaction and how that has modified the liquefiable layer, certainly.
Right. I guess the idea being, I'm sure something that you thought of, is that if you could go back and you could get properties, maybe you could find a way to correct what you've done here and see how close, maybe you could whittle away some of these other uncertainties, There
has been studies doing just that. I can't think of it off the top of my head. I think there's been some studies in Japan, investigating locations after an earthquake and seeing what the resulting changes in relative density are. They are there. I think my recollection is that they're relatively minor compared to some of the other uncertainties in our liquefaction triggering procedures, giving us sufficient reason to go back and do some of these follow-up subsurface investigations.
Thanks a lot for that. Thanks for the information. Great presentation.
Thanks.
So I had my hand up. Is it okay for me to ask a question now, Kristen?
Oh, yes. Yes, go for it. Sorry, I didn't see yours. Go for it.
Okay. This is John Stewart. Thank you, Mike. That was a great presentation. I've seen your advisor present on it many times, but I've never seen you, and I think you did a great job. My question has to do with the timing of liquefaction that comes out of these analyses, which seems to be a very important parameter from a modeling perspective. And my question specifically is, if you have a vertical array, as in wildlife, or you don't, like the site in Japan, there must be different levels of uncertainty in that time of liquefaction. And I wonder if you've thought about that and tried to quantify that in the different sites that you've investigated, and if there really is a difference in the uncertainty.
Well, there's absolutely a difference in the uncertainty, and I would say more so just in some of these case histories versus some of the others. Sites that are, let's see if we have one here. So sites that are initially relatively stiff and then liquefied, it's relatively easy using the Stockwell spectrum to pick out when that rapid shift in frequency content occurred. Sites that are initially very soft and then liquefied, sometimes it's really different. This Amagasaki is a good one. It was a very, very soft site, and this was a very strong ground motion. And liquefaction likely occurred during one of these first cycles. And we can look at the evolution of whatever intensity measure you want, whether it be PGA or Aereus intensity or these other things, the number of cycles of loading that evolve with time, and compare that to our liquefaction triggering curves to help us confirm that the timing of liquefaction does indeed match up with what we would expect the intensity of shaking associated with liquefaction. So there is significant uncertainty, or there can be, and that has some impact on what you would estimate to be the intensity of shaking at the time of liquefaction. Steve and Sam Sedaris have done a significant amount of work looking into this. In the uncertainty in liquefaction triggering, this timing-based approach certainly needs to be accounted for. And but we have tools that we can do that with the Stockwell spectrum. We've looked at statistics associated with, what's the when is the non-stationarity in the ground motion occurring? So there's statistics available to look at that sort of thing. So we haven't directly applied it to, for example, developing a triggering model, but there are possible ways of doing that.
Yeah, so there is a difference in your level of certainty if you have a downhole array or you don't, but maybe you haven't really, maybe it's hard to specifically say what the difference in uncertainty is. Is that a fair statement? There's other factors maybe that are more important, like the stiffness of the site?
Yeah, I'd say the stiffness of the site is more important. With respect to the intensity of shaking at the instance of liquefaction. I mean, when we have these relatively stiff sites, we can get it within, I'd say within a second or two of when liquefaction was actually triggered. At some of these soft sites, it might be much more challenging. Of course, the downhole array provides the highest confidence estimate. I mean, we can really narrow that within half a second or so of timing, or really the travel time between the downhole array and the surface array. But yeah, some of the stiff sites, I think there's more uncertainty between the stiff and the soft site versus the stiff site and the downhole array.
Okay, thank you.
And this is Steve Kramer. I'll add a couple things to supplement what Mike said. It's a difficult problem, and it can be very challenging to try to identify the time at which liquefaction occurred for some cases. For cases like wildlife, if you look at the, I don't know, Mike, if you can scroll to that Stockwell spectrogram quickly, you could see pretty easily when, just visually, when liquefaction was triggered. It's a pretty sharp decrease for Superstition Hills there. If you look at some others, even the Harbor Island one that you showed, Mike, it's the transition from higher frequencies to lower frequencies is much more gradual than that. And so to recognize what we're really seeing here is a change in the natural frequency or frequencies of the soil profile, and we're inferring liquefaction from that as the cause of the softening that appears to result to produce that change in frequency. There are some other interesting things here, Mike, with the time history for Harbor Island, or sorry, for the SDS building that you had showed at one point. Everybody can see at about 40 seconds or so, there are some really strong dilation pulses there. They're very asymmetric, and that instrument is right adjacent to a building, and I believe the building is supported on shallow foundations, and so there's a static shear stress in the liquefiable soil there that would tend to cause it to dilate more strongly in one direction than the other. And so this is a case I've always wanted to take a closer look at, but have never quite gotten around to. Also shown there in the upper two plots are a couple of the New Zealand Christchurch instruments where we know liquefaction occurred. And a lot of the New Zealand ones have been proven to Mike and I to be difficult to interpret because as Mike had indicated, the profiles were not that stiff to begin with. And so the change in frequency content is not as pronounced as it is for some of the other cases. And if we had some cases where, say in the San Francisco Bay Area, this type of situation where you might have some artificial fill on top of bay mud, the profile is soft to begin with. And so this kind of an approach is unlikely to work well there unless you had a downhole instrument or an instrument that was relatively close to but below the liquefiable layer. Scott made a comment about the effect of these dilation pulses on the response spectrum, and that is very true. The low period part of the spectrum can be dominated by these high frequency dilatancy pulses, and it's not clear to me that those pulses, because they can be so sharp, that a spectrum is really a very good representation of the characteristics of a ground motion for cases like that. Those are just a few comments that came to mind as I was listening.
I don't see any lingering questions in the list or hands up. So I think that wraps up all of our questions.
Okay. Well, great. I guess we can close it out then. So let me first thank SWRI for hosting this webinar and the future webinars as well. We'll have a number of webinars coming up in 2021. Many thanks to Mike. That was a great presentation. I think we all learned about these really special case histories that you've compiled for us. And I'm glad that there's more to work on. I think there's one in Alaska too, by the way, from that earthquake a couple of years ago. So thanks to Mike, and thanks to all of you for taking time to attend, and wishing you happy holidays.
Thanks, John. Take care.